Welcome back to this series on support vector machines. This is the final video, I think, that I'm going to be doing on the subject, and it's probably the one which is going to be most practical use, which is how to use SVMs in R. What I would say is, even if this is the only thing which is of interest to you, using SVMs in R, I'd really encourage you to look at the other videos, not just to get the number of views up on those videos, but because I'm always quite nervous of using any kind of machine learning data science technique if you don't really understand what's going on and why it's working and what it's doing. There can be a real temptation to use the wide range of models, which often have pretty straightforward interfaces, to get numbers out without really understanding what's going on, what it's doing, and maybe understanding what some of the pitfalls might be in terms of things like, say, overfitting. So I'd really encourage you to go back and look at some of the theoretical underpinnings of support vector machines, so you can see why what we're about to explain now, which looks very straightforward, why it works and what it's doing. So fitting support vector machines in R using the kernel method is really easy. You only need two packages to do this. Open XLSX2, which I've switched to using this now from XLSX. I find it loads things much more quickly. I'm much less likely to run out of memory. So it's apologies for steering you to XLSX in my earlier videos. This is the one I'm using now. And the other one is package E1071, which is a very broad data analytics package. It's got a lot of tools in it for some of the techniques I've used before as well, but it is the only one I could find which does support vector machines, and it does them very well and very quickly. So the first thing you want to do is you want to load these two packages. So assuming you've got them installed, which you'll all be familiar with from the earlier videos on how to use R, you then use library open XLSX2 and library E1071. Now, compared to the Excel analysis, where I was trying to make stuff as easy to visualize as possible, that's not something I'm so concerned with in R, so I'm going to use more dimensions. In particular, I'm going to use 4 variables, so G equals 4 for each firm, 50 firms based on the KNN data set. Here I've got the training data on the 6th worksheet. I've also got some test data on the 7th worksheet. And I've put the workbook in my working directory for RStudio. And what you see is under default there, whereas for KNN it was 0s and 1s, here it's +1 for a solvent firm and -1 for an insolvent firm. So this code first imports the data, then it makes sure the default column is a factor. And this means that it gets treated as a category, not a number in SVM, because there's a couple of different types of SVM that are available here. One is a regression-based one, and one is a categorization one. It's the categorization one that we want. We want to categorize firms rather than classify them numerically. And then it displays the results. So, how does this look in RStudio? Well, the code is there on the top left with the 2 library functions and the instructions to read in and display the data. And you'll see that's exactly what it does in the bottom right. And continuing down, you'll see the test data at the bottom. We've got the first firm which appears solvent and the second firm which appears insolvent. So that's the results that we hope to get when we are carrying out the analysis on those 2 test firms. Next, we need to fit a support vector machine, and we use the RBF kernel, which we discussed last time, with a C value, a cost of 1, and a gamma of 1 as well. We set the probability to true, and we need to do this in both the fit and the prediction, and then view the fit statistics. So first I create this object called SVM fit, and you see it's structured quite like a regression. Run the function SVM, and the function is default, explained by EBIT over assets, log of assets over liabilities, retained earnings over assets, and free cash flow over assets, based on the data from the training data file, using the kernel radial cost equals 1, gamma equals 1, and probability set to true. And then I just run SVM fit, and then I run the prediction afterwards on that object on the test data file, again with the probability set to true. So that's how the code looks in the top left. First, run the code for SVM fit, and it calls that function, tells me the parameters, SVM type, C classification. That's what I wanted. The kernel is, and the reason it does that automatically, you can set it manually, but the reason it does it automatically is because I set those defaults to being factors. The SVM kernel is the radial, cost is set to 1, number of support vectors is 32, which is quite a lot of support vectors from 50 data points. So as I said, the number of support vectors is large, and I think that's the neutral gamma means it's got similar weights to many of the powers, and also the low C means that the margin is quite soft, but the predicted power does appear to be quite good. If we look at what it suggests for those two training firms, it suggests that the first one has a 92% chance of being solvent, and the second has an 81% chance of being insolvent. That's pretty good, that's pretty impressive. What happens if you start changing the parameters? So you can either have, say, cost of 10 and gamma of 1, cost of 1, gamma equals 10. What does that do? Well, the first one, it doesn't seem to affect the first firm very much, but the ability to predict the second firm has got much worse. And if you go for a cost of 1, gamma of 10, well, there you've got materially worse ability to predict the first one being solvent, and it gets it completely wrong on the second firm. So you can see there that changing those two parameters does have quite a significant impact, and it is important, if you're doing this, to make sure that you do have some robust way of determining those variables first on your training set, with some sort of replacement approach to divide your training data into training and test sets, work out what your cost and gamma should be to give you your best results, and do that before you really approach some true test data sets. So you can see then that using SVMs in R is really straightforward. It's kind of scarily straightforward. The hardest thing there, I think, is about getting the parameters right for the RBF, if that's what you're going to be using, in terms of making sure that your cost parameter is correct and your value of gamma is correct. And the way to do that, as I say, is you take your training data and you use one of a number of different approaches to split that into training and test sets, to redo it over using different splits of the data, and try and work out what values of C and gamma work best, and just understand exactly what's happening as you're changing those values of C and gamma, and just be aware of any potential overfitting. But apart from that, it's really very straightforward indeed, and I think it's amazing looking at the complexity of what goes on under the bonnet with SVMs, that you can have a tool which works as well as this and works as quickly as this and is accessible as this. But having said that, I think you're always at an advantage if you understand exactly what these models are doing. So if you just come straight in with this one, please have a look at the other videos so you know what you're doing when you're doing this, and you can understand how it's working compared to some of the other approaches, such as k-nearest neighbour, or even just good old GLMs. But anyway, that is it for now anyway for support vector machines. I hope you've enjoyed this series. Please like it, share it, comment, subscribe, all the rest of it, and I will see you later with the next in the series of credit risk modelling videos that I am working on as we speak. Thank you very much.